we will begin the next technical session number 4. My name is Ramon Florentino Santos, instructor from the Electrical and Electronics Engineering Institute of UP Diliman. So before we begin with the first speaker of the afternoon for technical session 4, we would like to take a moment to recognize the generous support of the NEECECON sponsors. Firstly, Advanced Energy, Techmark Keysight Technologies, Embedded Silicon Technology Solutions Corporation, Meralco, Analog Devices Incorporated, Presidium PH Corporation, Road and Schwartz Philippines Incorporated, Alexan Commercial, Maker Lab, Samsung Electronics Philippines Corporation, and Challenge Systems Incorporated. So our first speaker would be Mr. Brian Yeo. He is a solutions engineer from Keysight Technologies, Singapore, and he is going to be presenting about the harmonized conformance and interoperability testing from Keysight and given the current trends in EV charging. The title of his presentation will be Testing Conformance and Interoperability of EVs and Charging Infrastructure. So let's give a big round of applause to Mr. Brian Yeo.
Hi, good afternoon, everyone. My name is Brian. I'm the solutions engineer with Keysight Technology, and I'm based in Singapore. A pleasure to be able to present a paper in this seminar over here. So the topic of this afternoon on my part will be testing conformance and interoperability of electric vehicle and charging infrastructure. Right, so that's the agenda that I have for my session. So I talk a little bit about the charging interface test challenges and then what Keysight Technologies is able to offer for the testing of the charging interface. And then, of course, I'll end off with a quick question and answers. So this slides over here shows the overall Keysight portfolio in the e-mobility solutions. So Keysight has test solutions for the charging technology, both at the infrastructure, meaning the charging station, as well as the electric vehicle itself. We also have test solutions for the electric inverter in the car, and also test solutions for the energy storages that goes from cell, modules, and pack. And we also have test solutions for battery management system. All right. So that is the overall test solutions that Keysight is capable of in terms of on the e-mobility space. And these are some example pictures of our customers' installations. So on the top left and on the bottom left, these are the test solutions for the charging interface, both for the infrastructure and the EV itself. So on the bottom left, that picture is the EMC compliance test for electric vehicle and charging stations. So electric vehicles and charging stations are required to meet the electromagnetic emissions as per other electronic product, like consumer product as well. And in the middle pictures, these are the installations for battery tests. And on the top right-hand corner, this is the test solutions for battery management system. And on the bottom right, this is the electric inverter test solutions. So my topic on testing of charging infrastructure is very close to this afternoon topic, which is on the energy. So as we understand that with the proliferations of electric vehicle, this has created a tremendous demand on the grid because you can see if electric vehicles, the battery inside there are getting bigger and bigger for the fact that the car itself requires longer driving range, and with a bigger battery pack within the vehicle, then obviously the next question is how long do I need to charge up the battery pack? And in order to speed up the charging process, obviously you require a lot of energy during the charging process. And with that kind of also reshape how the grid infrastructure is looking at right now. As Morocco has presented, there's a very different way of generating power, either from DER, distributed energy resource, which is equivalent to the variable energy resource. All right, and EV now is also considered as an energy resource because of the fact that it has a big battery pack in there, and the charging technology has advanced to the point where it could return the power back to the grid from the electric vehicle itself. So this slide just goes to show that the EVs are creating more demand on the grid, all right? And as a result of that, new ways of generating energy is required, and there will be more and more investment into grid-tied battery storage, all right? And more investments will be needed in renewables in order to cope with the demand created by the EVs. And it is also expected that there will be 20 million charging stations worldwide by 2025. And with that, the charging technology is also ever increasing to go towards faster charging. Like, for example, the CCS, the combined charging standard, we are looking at potentially 450 kilowatts of charging power. The GPT technology, which is the Chinese charging standard, they are looking at 900 kilowatts of charging power. And for the heavy-duty EVs, this refers to, for example, trucks. And in the mining industry, where the big mining vehicles, they are also undergoing a transformation of electrification. And these vehicles will require at least 1.5 megawatts in charging power. All right. So what is really important is that, if possible, we are trying to harmonize all the different charging standards, and this makes testing much easier. However, different region and different economical and political interests will generally prevent the harmonizations of one single standard worldwide. So what we are seeing is that there are many different charging standards in the world. Now, before I go into that, so let's just look at the few charging modes that are available today. The first mode of charging, obviously, is AC charging, where you plug the electric vehicle directly to the grid. This is now considered as obsolete because of the fact that there are many various hazardous conditions that can happen if we were to plug the EV directly to the grid itself. And then the second type will be what we call AC home standard charging, where you buy an electric vehicle and the electric vehicle comes with this what we call a charging adapter, where they can plug it in safely because it has a little control unit that provides some electrical safety protection during charging. And then there's the public charging, either the AC public charging or the DC public charging, all right? Now, for AC charging, the standards being used today are the IEC 61851 specification, all right? And this has been adopted for the standard charging for AC, all right? It's low cost and very easily available, and the technology involved for AC charging is also relatively simple, all right? There's no high-level communication. However, the charging power is typically low, maybe up to 20 kilowatts as the max, because the amount of current that can be pulled typically from a single phase is perhaps just 32 amps. And one of the big challenges that with AC charging is that with different regions, you get different line voltages, so that makes the implementation difficult. The second mode of charging is DC charging, all right? And even for DC charging, there are multiple standards available. And because of the fact that DC charging utilizes extremely high current, so some kind of high-level communication is necessary to ensure that both the charging stations and EVs are able to communicate and ensure that the connection is safe before energy transfer. All right, and typically for DC charging, I think today, maybe not so much in Philippines. Today I've been here in Philippines since Monday. I've been in Cebu and then back here, but I don't see a lot of charging stations. But if you, within Southeast Asia, for example, in Thailand or in Vietnam or even in Singapore, you'll find that there has been a lot of high-power DC charging. I think the common ones are 120 kilowatts. I think I've seen some that are as big as 360 kilowatts. And these will require a lot of power. And these are the DC chargers that will be up and coming because of the fact that we do not want to be sitting down there waiting for the car to be charged up. We want our EVs to be the same as an internal combustion engine, where you go in there, you put in your fuel within less than a minute, and then you're ready to go. So if you look at the world, you'll find that there are many different standards being utilized. For example, in North America, where Tesla is dominant, they have their own standards. But however, for DC charging, it is typically the CCS Type 1 or the CCS Type 2. This is found in North America, in Europe. And then in Japan, we have the CHAdeMO standard. And then for the Chinese, they have the GPT standards. And then now, in addition to that, we also have a CHAoG standard. This is a combination of the Japanese standard and the Chinese standard to allow higher power of charging. All right. And then finally, just recently, we also seen the release of the North America charging standard, which is basically Tesla opening up the charging interface testing standard for the rest of the world to use. Oops, sorry. So one of the things about e-mobility is that it is really important to have your vehicle and charging station being able to interoperate together, because one of the things that we don't want is that your battery of your electric vehicle is low and then you drive your car up to the charging station, and when you're plugging in the charger, you just simply refuse to charge. So this is why testing of the charging station and the electric vehicle is really important to ensure that it's able to interoperate. Only then would e-mobility be able to scale, and we'll see higher adoption of electric vehicle and electrifying of the transportation in order to hit the net zero emission goal that is pledged by governments around the world. So in the past, the testing is very simple because of the fact that there's only a few models of electric vehicle and charging stations. So what manufacturer would do is they would simply go out there and buy all the charging stations, and then they will cross-test against one another. But today, we have so many different brands, and even a particular brand, they have so many different models of charging station in electric vehicles, so it's no longer possible to do this kind of testing, all right? So what is really needed, and also in the name of good science, is to have a universal test device where all the electric vehicle and charging stations are being tested using this universal test device, all right? Only then when you have any problems or any issues during the testing, then you know that this is a problem with the, either the electric vehicle or the charging station only, okay? And for robustness in the test, you want to ensure that you'll be able to test the communication as well as to the power level, all right? So this will ensure that your test is sufficient to ensure that the devices, the EVs and the charging station will be able to interoperate against one another. And if you look at the various specifications available today, all right, starting from 2014, when the early specifications of the IEC standard is available. All right. So what I'm trying to say here is that even if you design the electric vehicle or charging station according to the standard, it does not guarantee interoperability. It just simply means that your system design follows a baseline design. All right. However, to be able to interoperate, you need to ensure that the electric vehicle and charging station are tested based on a set of rules, and this is where the test specification is something that you want to look at. So here you can see that the specification only defines the system topology and the safety requirement for EVs and charging station, whereas for the communication itself, it is necessary to check on the adherence of the communication to the standard. This will then ensure that when the device, when the charging stations and the electric vehicle get together, they are able to talk in a common language, and a common language that both the charging station and the EVs are able to understand. And there's no breakdown in the communication which will interrupt the charging process. Now, KISA is a core member of CHARIN. CHARIN EV is actually the organization that is responsible for the CCS standard. The CCS stands for Combined Charging Standards, which is the charging interface for DC Type 1 and DC Type 2. All right? And KISA is a core member of CHARIN organization. Being a core member, KISA has the responsibility to define test methodology in the goal of achieving interoperability. So once this test methodology gets accepted by the organization, then this becomes the test specifications being published by Charin EV. And this slide here just to show an overall portfolio of the available tools from Keysight for testing the charging interface. And these tools will map into various development stage, all the way from R&D to production to maintenance. So on the left, we have our charging communication interface tester. So this little box on the left is meant for EV and EVSE manufacturers when they are designing their charging circuit, where they are only interested in the charging communication without energy transfer. And if you need to test up to energy transfer, then we have our charging discovery software and charging discovery system portfolio, which is in the middle. All right, so you see there are three different systems. One is the little silver stainless steel, and then a middle box, and then two big boxes at the back. So these are our charging discovery system that can be used to test the EV and the charging station. And then at the bottom, these are Keysight power system that will emulate the power sources or the power sink during testing, depending on whether you're testing the charging station or EV. And then lastly, on the right, we have a protocol tracer. Right, this is a box that can actually listen to the communication between a car and a charging station, so that then you would try to understand the communication breakdown to find charging interruption problems. All right. So these are the three main versions of the charging discovery system: the SL1040A portable series, the SL1047A high power series, and then the EMC series as well. All right, and the three different use cases for the charging discoverer system, the CDS in short. Here we are trying to test the EV. So we have the charging discovery system performing the role of a charging station, and then from there you can test out the various charging networks as well as the circuitry, or also to test for conformance and interoperability of the electric vehicle. And then the next use case would be when you're testing the charging station. Again, similarly, here you are trying to test the charging circuit as well as functional tests, conformance or interoperability, or end-of-line testing. And then the last use case would be to check for charging interruptions or analysis of interoperability issue, where you have the charging discovery system in the middle between the charging station and the vehicle itself. And this is a test environment for electromagnetic compatibility. So I've taken this diagram from the IEC 61851 on the EMC test setup requirement. So Keysight actually released a different version of the charging discovery system so that it can be used in the anechoic chamber during EMC tests, because if you look at the IEC 61851 EMC test setup, this requires the EV simulating equipment to be in the same anechoic environment as the device under test. All right? And this is the software that will be used to control the equipment. Right, so it's an all-in-one software where it allows you to control the system, either to perform EV or EVSE emulation, or you could also look at the data that has been collected during tests. You can look at the communication, as well as it allows you to develop different test scenarios. And for conformance testing, we are using the Spirent TTCN3 workbench. So Spirent is a company that is very well known to supply the TTCN3 workbench. It is kind of the standards for conformance testing. So Keysight is using this TTCN3 framework to offer conformance test library. So this test library could be used for the DIN standard, the 70121, or the ISO standard, the ISO 15118. Okay. And during the test, if you require energy transfer, then Keysight has various power systems to work together with the charging discovery system. This could be the high power series, where we offer up to 300 kilowatts, plus minus 600 amps, up to 1500 volts DC. Or we have some mid-power series and low-power series, so it really depends on what is the power level that you want to test, and Keysight has a appropriate, what we call power emulators for the power source and sink. We also have AC power system, where these serve as a dual role. It can serve as a grid emulator if necessary, all right? Or it could also be used as a AC load as well if you're testing for AC charging system. So Keysight has been supplying our test solutions to more than 100 customers across the world. All right, they could be car manufacturers, they could be charging station manufacturers, also test facility as well. So Keysight has been very successful in providing test solutions for these groups of people across the world. And that's the end of my presentation. Any questions? If not, thank you for your time and have a good rest of the day. Thank you.
Thank you, Mr. Brian Yo, for your presentation. So now I would like to, final question, are there any other questions from the audience? None, okay. I would like to give this certificate of appreciation to Mr. Brian Yo for sharing their invaluable insight and work on testing conformance and interoperability of EVs and charging infrastructure during the NEECECON 2024 conference. Given this day, July 2024, signed by Dr. Lu Andrew Tria. Our next speaker is Engineer Leo Alentayo. He is the Senior Technical Specialist for the EPOB project of the University of the Philippines, Diliman, and the Department of Science and Technology, as well as being the CEO of Charge EV Technologies Incorporated. He will be talking about the development and technical research regarding the e-mobility in the Philippines. The title of his presentation is Electric Vehicle Prototyping and Testing through the E-Mobility Research and Development Center.
Thank you very much, Sir Soran, and great afternoon to everyone. Okay. Yan. So again, good afternoon. I'm Leo. I'm an electronics engineer, and I'm part of the Power Electronics Laboratory of UP EEEI, and also the E-Mobility Research and Development Group of the same institute. So basically our group, at least for our section, we basically deal with the electrification of transportation or land transportation. So later on, the next presenter will be discussing about the electrification of waterways or vehicles for our waterways. So for this presentation, just a short background. So back in 2022, so the EVIDA, or the Electric Vehicle Industry Development Act, was actually passed into law. So this law basically solidifies the effort of the Philippine government to support the transition of the country to renewable energy or sustainable energy vehicles. So the highlight of the law, as you can see here, it already presents a mandatory 5% of EV share when it comes to corporate and government fleet. So the law already mandates the transition of at least 5% share of our vehicles locally into electric vehicles. Because the main objectives also of the law is, at least for the transport sector, is to reduce our dependence on imported fossil fuels for our transportation sector. And together with the EVIDA is actually the CREVI, or the Comprehensive Roadmap for the Electric Vehicle Industry. So the CREVI, basically, it provides the flesh to the EVIDA in terms of the roadmap of the government, the specific action plans that the different agencies are going to undertake in terms of the implementation of the EVIDA. So specifically, the CREVI outlines the action plans for the EV industry, specifically for the electric vehicles and electric vehicle charging stations, the manufacturing, human resource development, and also research and development. So from our end, we work on number 4, which is basically research and development. And today, I will be discussing actually just the overview or the highlights of the program, especially through the NEECER e-mobility program and the electric public utility bus program. So the program is actually huge. So given the time, I'll only be able to discuss basically just the tip of the iceberg, just to give you an appreciation or overview of what we do. So basically, the NEECER e-mobility program is actually a collaborative effort through the collaboration of the Department of Science and Technology, UP Diliman, and the Cagayan State University. So on the top level, the program actually wants to design, develop, and manufacture local electric vehicles that can already be assembled and manufactured here in the Philippines. So I'm talking about the body, the chassis, suspension, the frame, and all of the electronics. As much as possible, the program wants to design and develop those vehicles locally. And for the NEECER e-mobility program, the part of UP Diliman is actually through Project 2. So we are basically in charge of the development and assembly and testing of the whole electrical and electronic system of the vehicles. Okay, so I'm jumping actually to the summary of this presentation for you to be able to already get a glimpse or an overview of the output that we were able to give for this program. So these are actually just 3 of the different prototypes of e-trikes. We call it electric tricycles or e-trikes here in the Philippines. So these vehicles are in a way unique to Southeast Asia or the Asian region because they are used for the so-called the first or the last mile connectivity. So the counterpart of these vehicles are what we call tricycles. So they're generally powered by gasoline. So for the program, again, we were able to develop 3 prototypes as an alternative for our tricycles. So these here are actually 3 electric tricycles. So the one on the rightmost, actually in collaboration with a local company called EVWealth. But for the first 2, the prototype 1 and prototype 2, these are actually holistically designed and developed from the ground up. So, and actually just to also highlight, as you can see, the body composition, especially with prototype 2, I just want to mention the team from CSU also implemented the use of abaca fibers for the construction of the body of these e-trikes. So basically, we also want to showcase and utilize our locally available raw materials for the production and construction of the body of the e-trikes. Already mentioned that because further down the presentation, we'll be only discussing about the electronics. So baka makalimutan. Okay, so if you're watching the news, of course, so lately, it became a hot topic here in the Philippines regarding the regulations on where these types of vehicles, whether you're using an e-bike, a tri-bike, or an e-scooter, in terms of road access, it was in a way a hot topic in the news. But actually, even before that incident, there are already regulations issued by the LTO in terms of the accessibility or road access that will be given to these types of vehicles. So for the vehicles that I showed earlier, these are categorized as L4 vehicles. So they are symmetrical vehicles. And L5 are the non-symmetrical vehicles that are also electric vehicles. So again, this is just a rundown of the restrictions and regulations when it comes to these types of vehicles. So for these vehicles, although motorcycle helmets are not really required, so appropriate driver's license and registration of the vehicles are still required. So just keep those in mind. Okay, so again, aside from the holistic design of the vehicles, on our part, the Project 2, we were able to develop the main electronic components of our e-trikes. So these are the 3 main, basically huge chunks of those components, namely the VCU, the BMS, and the motor controller. So for this project, we were not yet able to integrate a locally designed and fabricated motor controller, but that will, or motor, electric motor, but that will be addressed down the road. So basically, the VCU, of course, is the brain of the vehicle. It controls all of the vital functions of your EV. And the battery management system, by the name itself, it not only manages the battery, it monitors the functionality of the batteries, and then also provides a great level of protection for the batteries. Because for electric vehicles, especially the ones using lithium-ion, so the cost of the batteries constitute about 30 to up to even 50% of the vehicle cost. So that's why we really need to provide a safety and reliability when it comes to our batteries. And of course, for the motor controller, this is the one that converts power from DC to AC and drives the motor. Okay, so this is just an overview of the methodology and development flow that we are using. So so even before we go into the development of actual hardware, so these are the software that we are already using to basically design, simulate, and calculate the level of power, so the level of communications and complexity that we need to include in the design. And of course, for hardware and software implementation, so these are the software that are being used. For design verification, we heavily use ANSYS for this. And for when we already have the vehicle at stage 4, we do the testing and pre-certification of the vehicles for the components in PEL. But for the whole vehicle, we use the facility in EPDC, in Bicutan, and also in Tuguegarao, the EMRDC, or the Electromobility Research and Development Center. Okay, so as I mentioned from stage 1, so even before we do any hardware development, so the fancy term for this is actually digital twin, but we refer to this as the model. So even before we decide the CAD for the vehicle, even before we decide the level of power, the size of the battery or the capacity, we do simulations and vehicle modeling inside MATLAB Simulink. So basically through this, we are able to already develop a digital model of the vehicle. So, and not only that, we are able to actually simulate also the road conditions that the vehicles or that the vehicles will be used. So we'll be able to, like for example, if it's going to be used in Baguio, where you have a lot of uphill, we'll be able to adjust the motor power and the battery size to accommodate that specific conditions. And this is just an overview of that package. So this is a very methodical process, even the integration of air conditioning. So we'll be able to model that and also see the effect of air conditioning to the vehicle mileage or efficiency. Okay, so for design verification, as I mentioned, we use ANSYS. So we use these two components heavily, the SI wave and the ISPAC. So the ISPAC, of course, for the thermals, so the thermal performance of the electric vehicle components. And for SI wave, we use that for signal integrity, especially for the evaluation of EMC for our PCB design. Okay, so when we already have the components, the prototype, also it's great that Keysight was able to present earlier and touch on some of the standards when it comes to testing. So we do, or basically we perform pre-certification testing for the prototypes that we are able to develop. So we do this in EPDC. So this one specifically is for the EMC testing, or electromagnetic compatibility testing of the battery system and the BMS. Okay, we also do thermal and humidity testing. So we subject the components that, the prototypes that we did to extensive testing to high temperature and high humidity. And, ascertain that they will perform on actual road conditions and actual environmental conditions. We also perform ESD, or electrostatic discharge testing. This is basically high voltage testing for the components to ensure that they will not fail if ever a high voltage comes in contact with the electronic components. Okay, so as a whole vehicle, we also perform EMC testing, as you can see here. So we perform both radiated and conducted testing, both for immunity and emission, to ensure that the vehicles that we develop here are conformance to international standards. Okay, so aside from the EMC, ASD, and thermal testing, of course, we perform dynamometer testing. So even before we test the vehicles, the prototypes on the road, we'll be able to test it on the laboratory stationary setup. So we are able to get the maximum power, the mileage or the performance of the vehicles even before we deploy them on the road. Okay, so this is just one of the highlights of the laboratory testing that we did. So these are three graphs. Basically, the upper one is the no-load performance, and then the half-load, and then the full load. So as you can see here, we are able to characterize the performance of the vehicle in terms of its mileage. So you can see on the left-hand side, it's kilometers per kilowatt hour. So the higher that number, the more efficient the vehicle is. So you can see here, we were able to characterize also on different speeds. So we are able to say on what speed you can operate your vehicle, and you will be able to get the optimal mileage out of it. Okay, so in addition to this project for the e-trike, currently we're doing another project with DOST again, and also CSU. We're doing the electric public utility bus project. So yeah, so same methodology that we applied, from design and simulations to design verification and to testing. So this time it's a much bigger vehicle. So we're focusing basically on the vehicles that are used for public transportation. And this is just an overview of the specifications, target specifications that we are going to deliver for these vehicles. And hopefully, by next year, you'll be able to see this prototype bus either on EDSA Carousel or the Quezon City bus service. So I think that's it for this presentation. And I think in summary, we are doing the research and development efforts to basically design and bring the manufacturing of these electric vehicles here in the Philippines. So again, thank you very much and have a good afternoon. Thank you.
Thank you, Engineer Tayo. Are there any questions from the audience? Well, I have one question. Given the prototype, what do you foresee for the cost of the e-trikes, given that cost or price of the vehicle is a common source of contention for PUV operators?
Very good question. Actually, what we have right now is the prototyping cost. So typically for the electric vehicle, for the bigger model that you saw earlier, the prototyping cost for that is around 400 to 450,000. But remember that the prototyping cost is always high. Right now, the status of this technology is that we already have a licensed manufacturer for the e-trikes. So basically, if we get more number, we'll be able to bring the cost down, the manufacturing cost, and in turn, we'll be able to match or even lower the selling cost of the e-trikes. That will be hopefully in parity with the selling price of our conventional tricycles. Thank you.
All right, are there any other questions?
Yes, I have a question, just a general question. So you mentioned having a digital twin in your design process, and you've developed many generations of electric vehicles. I'm just curious how you also tweaked your digital twin as you have been iterating your prototypes. Does it generate its sensors within the simulation, or do you use actual sensor data to interface with your digital twin?
Yes, thank you for that. So again, we have, aside from the digital twin, we have the luxury of having the vehicle dynamometer inside the laboratory. So basically, we don't really need to drive the prototypes on real roads to get the actual data. So basically, what we do is do the actual testing on the dynamometer, collect all of the data related to that, and then we bring that back to the MATLAB model. And then we do the tweak, and we do the alterations on the parameters for us to be able to match, for example, the power curve, instantaneous power curve of the vehicle, and then the match also the mileage or the efficiency of the vehicle. And through that way, it's actually a feedback system that we can get from the actual prototype, and we bring that back to the MATLAB model.
Okay, thank you.
Thank you.
Are there other questions from the audience? If none, I would like to give this certificate of appreciation to Engineer Leo Alantayo for sharing their invaluable insight and work on electric vehicle prototyping and testing through the E-Mobility Research and Development Center during the NEECECON 2024 conference, given today at Novotel, Quezon City, signed by Dr. Lu Andrew Tria. So our third speaker for this technical session is Engineer Rovina Janel Tayo. She is the Senior Technical Specialist for the E-Ferry project of UP Diliman and Department of Science and Technology. She is also the COO of Charge EV Technologies Incorporated. She will be talking about the techno-economic optimizations involved in the planning of an electric ferry through the Pasig River. The title of her presentation is a methodology on the techno-economic evaluation of electrification of an inland waterway passenger ferry. Sorry.
Thank you for the introduction. Again, I'm Janel Tayo. I'm also part of the E-Mobility R&D group of UP EEEI. And I'm here more of to actually report the deliverables that we had for our DOST-funded project entitled Design of Electric Boat for Inland Waterways to Address Urban Congestion. So these are my teammates for that project, and I'm going to report more of our outputs for that project. So the main motivation really for this project is that the shipping industry contributes 2.5% of GHG emissions worldwide, and the International Maritime Organization aims to lower this to net zero emissions by 2050. And one of the possible solutions for that is really the electrification of the fleet of marine passenger ferries. Why passenger ferries? Because passenger ferries are actually prime candidates for electrification because there is already a set route. Meron na tayong set route dun sa mga ginagamit natin na passenger ferries, meaning you already know or expect kung ano yung magiging performance and route ng ferry natin. And through this project, we actually explored retrofitting of existing passenger ferries, particularly in the Pasig River ferry system. This has 4 objectives, mainly to determine the potential for emission reduction, retrofitting design for each electrification configurations, estimate the energy demand through simulations before we actually spend money on buying equipment and on the retrofitting itself, and of course, to determine the techno-economic feasibility of the retrofitted design and the deployment of charging stations. So these are the framework or the steps that it took us to be able to evaluate each electrification configurations for the fleet of passenger ferries. As mentioned, we chose the Pasig River Ferry system mainly because it's the most convenient location for us, and it already has the system in place in their Pasig River ferry fleet. So what we did was actually to gather the operational data from that location. So, for example, we were able to verify that the round-trip duration is 2 to 3 hours. There's an average docking time of 30 to 45 minutes. And the fleet size is actually 7 55-seater passenger ferries. Furthermore, we deployed surveyors so that we could get the real-time GPS data from the ferries and in turn output a voyage cycle that we can use in our simulations. And this is the actual voyage cycle that we were able to get, and also measure the fuel economy of the existing fleet. So what we measured actually is that the existing fleet has a fuel economy of 2 to 2.3 liters per kilometer. Aside from that, we also looked at the different accessible charging, possible charging ports that we could actually deploy along the route of the Pasig River Ferry. So these are the 4 locations that we saw would be most appropriate for the deployment of the charging stations, mainly because the ferry are actually spending their time on the docking, spending an average of at least 30 minutes of their docking time through these different stations. So the 3 electric propulsion configurations evaluated in this study is shown in this slide. First is the purely battery electric, wherein you're only getting your energy from the batteries. Second would be the diesel generator and electric motor. And third would be a hybrid of the battery and the generator. So most of the methodology that was used in this was actually from one of our key teammates, which is our naval architect, Cheryl Jokdo. And she actually introduced us in how we can model the ferry in order for us to determine the powering requirements. So the first step is actually to get the hydrostatic calculation. Through this, we were able to determine the hydrostatic characteristics such as displacement, wetted area, draft measurements, and center of buoyancy. We used the MaxSurf software and the Rhinoceros software, most commonly used by naval architects, to be able to do this. After which, we were able to simulate the component placements of the different electric configurations. So for this one, this is for the battery electric component placement. As you can see, the blue components over there are the AC motor and the battery bank. And then the diesel generator and electric motor component placement, wherein, if you can see the red box, that's the size of the diesel generator. And we actually used, through this, we actually used counterweights, remembering that we have to check the stability of the ferry also while we are placing the components. And for the hybrid one, the counterweights, previously with the blue color, was actually replaced with battery banks. So all of these modifications were taken into consideration in the estimation of the weight per configuration. And also, for all of the configurations, we assumed that the ferry is operating under full load conditions, meaning 55 passengers plus 3 crew members. And upon assigning the weights and placement of the electric propulsion system within the hull, stability calculations were done using MaxSurf and ANSYS Aqua software to determine the metacentric height per configuration, which provides an evaluation point for the stability. According to the International Maritime Organization, the recommended metacentric height, or the GM value, for inland ferry is between 0.5 meters to 1.5 meters. The powering requirements in kilowatts versus the different speeds of operations were determined after the modifications were considered as shown in this graph. by computing for the total resistance, including the frictional, air, and wave-making components. The red line represents the generator and hybrid case, which show that the highest powering requirements compared to the blue curve, which is the battery electric case. So we also use this powering requirements and the 45 kilometers reference void cycle that we were able to gather during the data gathering phase to be able to estimate the fuel consumption or the energy consumption through MATLAB Simulink. And the results show that for the base case model, our simulated fuel consumption was found to be 104 liters, equivalent to around 301 kilowatt hours of equivalent energy. And the resulting simulated fuel economy is actually 2.3 liters of consumption per kilometer, which actually goes back to what we gathered on the actual fuel usage of the ferry. So our validated data and the simulated data actually matched. And for the battery electric case, there is an increase in the weight, in the total mass, therefore also an increase in the wetted surface area and an increase in the power. And what we measured to be the simulated energy economy is 7.3 kilowatt hours per kilometer. And then for the diesel and hybrid, since they have the same mass and the same hydrostatic calculations, these are the resulting values. So all of these values, we are going to input in the techno-economic analysis in order to determine the cost of energy. So this is the final specifications of our proposed retrofitting for the battery electric ferry. And actually, we also simulated what it would look like if we deploy 4 charging stations, 1 in Napindan, 2 in Guadalupe, and 1 in Escolta, with 7 retrofitted battery electric ferries so that we can see if the operations will be feasible. So this video shows where the electric ferries will be charging, where they are intersecting, and we have determined that at the Guadalupe station, there will be at least 2 simultaneous charging transactions. So after which, all of those inputs that we were able to verify and the simulations that we were able to generate, we now use as inputs in our techno-economic study. We're in the voyage cycle, the energy estimations, and the fleet management model that we did, we assigned cost estimates. For the capital cost, given that there are 7 retrofitted battery electric ferries, there are 3 key locations for the charging stations with 4 total charging points, this would be the capital cost. This is considering that there are still 13 locations, 13 stations along the Pasig River ferry route. So as you can see, the battery electric ferry or the battery electric case has the highest capital cost. And the lowest capital cost is still the diesel ferry. For the operations and maintenance, so the key assumptions here is that it's 20 years of service life, 7 ferries, and then we use the simulated values of the fuel economy and the energy economy, and then the personnel is proportional to the number of charging infrastructure, or so that means that when you have the diesel generator, the hybrid and the battery electric, there would actually be more personnel that you have to employ. And as you can see here, that even with complete replacement of the batteries and replacement of the generators, shown by the peaks in the graph, the battery electric ferry, the orange pala yun, di pala red, has still the lowest O&M. Among the different cases. And this also translates to the emissions. Pinakamababa yung emissions for the battery electric compared to the hybrid, the generator, and of course, pinakamataas yung sa diesel ferry. And this also translates to the total cost of ownership, wherein the diesel ferry, the first one here, has the highest cost, and battery electric has the lower cost, greatly dictated by the pink color, which is actually the cost of energy, and the green color, which is the cost of emissions. Yan. So Tama lang. So this is our conclusion. Battery electric had the least energy economy, least displacement and mass, and the lowest draft measurement out of the 3 configurations. And this also has the least total cost of ownership despite having the highest capital cost. But there's also one thing that we realized during the conduct of the study. We are greatly limited by the existing design of the ferry. So ferry retrofitting is generally feasible but may not be the most efficient solution due to the limitations in space. For example, the Pasig River Ferry actually uses a monohull design, which is not necessarily the best design for a shallow river. So we conclude that hull shape and type also contributes to the design efficiency. So that's all. Thank you.
Thank you, Ms. Janelle Tayo. Are there any questions from the audience? I guess I have one question. Given the charging and powertrain of land vehicles, what are the major difficulties introduced by having the ferry in the water? Is that too different from the charging system and powertrain system of a land vehicle?
Thank you for that question. Actually, there is a great difference. Number one being the cost of the equipment. Since we are talking about higher IP ratings compared to land-based charging stations, we definitely see that the deployment of charging stations in river systems, in shore systems would be more expensive compared to the land-based systems and more subjected to safety regulations.
I'm just curious about the response of the LGUs along the Pasig River. How are they helping, basically?
Actually, MMDA has been a very good partner in this. We are actually already at the second phase of this study wherein we're going to prototype the ferry. And there is already design in place. There's already a definite charging location in place. So they are closely working with us and they are very excited with the project.
Are there any other questions? If none, I would like to thank Ms. Rovina Janelle Tayo. And I would like to give this certificate of appreciation for sharing their invaluable insight and work on a methodology on the techno-economic evaluation of electrification of an inland waterway passenger ferry during the NEECECON 2024 conference, signed by Dr. Luandro Tria. Thank you again. Our fourth speaker for today is Mr. Arvin Escoltero. He's a research fellow for CHED projects and a PhD student at the Electrical and Electronics Engineering Institute at UP Diliman. He specializes in power electronics and battery technologies. He will be presenting about his research on the hybrid system of fuel cells and lithium-ion batteries and its management as a robust power supply for telecom base stations. Yes, Mr. Arvin Escoltero.
So, hello and good afternoon, everyone. So, my name is Arvin Escoltero, and I'm here to present our study, which is a collaboration between Department of Chemical Engineering at saka yung EEE PEL. So, the title of the study is Bandwidth Optimization of Load Following Controls for Fuel Cell and Battery Hybrid Power Systems in Telecommunication Base Stations. So a little introduction about fuel cells. So fuel cells are, well, they are a energy conversion device that converts hydrogen fuel or maybe sometimes another source of hydrogen like methanol into electricity. And their byproducts are just water and heat. Now, so unfortunately, there are also some shortcomings with this technology. One being the voltage, which exhibits a high change in output voltage as the power changes from 0 to full power. And it has a weakness in frequent fluctuations in the output power, which contributes to more degradation as it progresses. So a solution to this is to hybridize it. Connect a battery there at the bus voltage that it will serve as the one that will capture the transient load requirements. And unfortunately, it will be an added cost to the system, and battery will still degrade even when partially charged and discharged. So optimizing the lifespan of the power sources will involve allotting which part of the power spectrum will be given to the battery and which part will be given to the fuel cell. So power sharing optimization, so allocating the power demand. So as we can see here on the right side, this is a load profile of a telecommunication base station. Although it's not that erratic as compared to electric vehicles, it still has some fluctuations throughout the day and even every second as the demand of communication changes. Now, so system health must be maximized while fulfilling the output requirements, where the output bus voltage must not dip at certain levels where the communication substation will shut down. So there are gaps and shortcomings. First is the optimization studies are usually involved in EVs because, well, that's the trend. And the fuel cell substations, fuel cells in stationary applications are usually just using rule-based approach, which is the cycle charging, where you charge the battery at full capacity and shut it down, and let it drain and sustain that bus voltage. So what we propose is to use the load following controller, which instead of utilizing that standard cycle charging approach, the fuel cell will follow whatever the output demand is required. Of course, you don't want to make it too fast, otherwise it will degrade too fast. So the DC-DC converter must be configured as a current source for this because the battery will maintain the bus voltage. And what we see is an integral controller is more than enough to control the fuel cell's output current because we don't want it to actually respond too fast, right? So adjusting the controller gains, we can actually control the bandwidth and the response of our fuel cell. And the system performance is, of course, finding which part of that bandwidth will it optimize in operation. Specifically, the fuel efficiency, degradation, and the operating cost. So we modeled the system and simulated it in MATLAB, Simulink. So we utilized the SimScape toolbox there, which has a fuel cell and battery model already. So it's just a matter of tweaking it to the way that is actually useful for us. So for the fuel cell, we utilize that model. We entered the parameters, but for the battery, we actually opt to use the table-based approach because the resolutions are just 1 second, and that won't actually be that much detail for the batteries. And of course, we want to simplify it so that the computations and the resources used will not be that much. Now, so what we added in the model is the degradation because we want to actually find the amount which is degraded because it is prone to changes right here from utilizing the load following approach. Now, so there are 3 major sections in the degradation of the fuel cell. One is the on-off cycling. So every time you turn off and turn off the fuel cell, it will add to degradation. We have duration-based degradation. The moment you turn on the fuel cell, it will already start to degrade by some amount. When you cross the overloading section, it adds another degradation. Underloading, another degradation. And of course, load changing part, which will follow the output load, adds another degradation. So actually, there are a lot of complexities in the degradation mechanism of the fuel cell. And another part of the degradation is the battery degradation, since we want to measure it to the point that we will not cycle it from max to minimum. So we want to create this model so that it will actually account for the AH throughput of the discharge of the battery instead of number of cycles. So here are our source parameters for our fuel cell. So we sized this, but that was another study, so I didn't include that much detail here. It would be too long. So we use a 4 kilowatt PEM fuel cell for the battery. We used a lithium ion because of the advent of many EVs. There are a lot of second life batteries available, and they're very cheap. So we use that instead of VRLA lead acid batteries. So we characterized the performance. So for the fuel cell, we checked which setting for the integrator would create a stable response, and which part would be too slow already that it will drain our batteries. So as we can see here, we used -20, -40, and -60. So they had that response. Fortunately for the -80, which is our slowest response, it already drained our batteries before it reached that set point. So, okay, but we override the program to see if what is the output fuel cell current for that. And we can see the green part right there, it's very smooth. Actually, that's the type of response ideal for the fuel cell. So we modified our algorithm to actually start. So we saw that the weakness was in the startup. So when you start it up, it already drained the battery. So what if we just start it up at max speed and then eventually slow it down in the later parts of the run? At least we can consider that part where it will have a slower response. Maybe it will be okay in the later parts. And we also introduced a fuzzy controller. What if it will be more dynamic instead of that step response? So here are our results. So as we can see, again, it's very smooth already. Unfortunately, it overshot to 1 this time. So again, if we increase the battery further, it will add to a capital cost, and it will be another issue, another problem for that. So it's another consideration, maybe consider for the later parts of the study right there. But for the other parts, yeah, we have that response for the faster response and for the fuzzy. So lastly here, we have the operating cost. So we compared the different load following approach, the acceptable ones, with the cycle charging approach. So as you can see there, a reduction of around $50 in the operation after 4 days when you compare the cycle charging approach with the load following. Unfortunately, when it comes to varying the different bandwidth, the speed of the controller, you can see there's little to no difference there, maybe a few errors, but it's not that significant. So actually changing to load following will already create that much benefit, but when it comes to optimizing it in terms of bandwidth, unfortunately, there's not that much. So actually setting it to load following at a certain stable response would actually benefit the system as is, and further optimization of it might be a bit not that much beneficial. So for conclusion, so utilizing an integral controller is more than capable of implementing the load following control, since we want a slow response. Power fluctuations in telecommunications base stations, well, it's not that erratic compared to electric vehicles, so load following is an acceptable choice for the controls. It will introduce less stress to the battery, allowing longer life and less maintenance replacements. For efficiency, yes, it also improved because there is less excess power that will go to the battery and will require the cycle efficiency. using load following controls instead of cycle charging will allow for better performance and overall less operating costs. And as long as the system is stable and the batteries are not drained, there's no significant difference in varying the bandwidth any further. And I just want to give thanks to our team, Project Cypher, the Chad Picari project, and I'm involved in. Thank you, everyone.
Are there any questions for Mr. Arvin Escaltero? I guess I have one question. Can this optimization be generalized to other kinds of loads? What kinds of loads are most similar to the one you studied, which is telecom base station?
Good question, and actually I want to consider that in future studies where I will introduce other load profiles specifically for stationary applications. No? So, diba, there are a lot of studies involving mobile and automotive applications, but for stationary, we want to actually explore those involving off-grid applications. Maybe it will lead to better, well, most likely we will expect a different result from that. Different size, maybe different bandwidth would be more optimal, or maybe rule-based approach will be better. I don't know. Maybe we can explore that further.
Thank you again, Mr. Arvin Escaltero. Now I would like to give this certificate of appreciation for sharing their invaluable insight and work on bandwidth optimization of load following controls for fuel cell battery hybrid power systems in telecommunications base stations. Okay. Our next speaker is Mr. Juan Glicerio Manlapas. He is a research fellow and master student from the Electrical and Electronics Engineering Institute of UP Diliman. He specializes in power electronics and battery technologies. He will be showing his research on the optimization of the usage of hybrid fuel cell and lithium batteries as telecom base station power supplies. The title of his presentation is Optimal Sizing of Hybrid PMFC Lithium-Ion Battery Power Systems for Telecommunication Base Stations.
A pleasant afternoon to all our distinguished guests here at NEECECON 2024. My name is Juan Guserio Siman Lapas, and on behalf of all of my co-authors and colleagues here, it is my pleasure to present to you our study entitled Optimal Sizing of Hybrid PEM-FC Lithium-Ion Battery Power Systems Using Rule-Based Cycle Charging Algorithm for Telecommunication Base Stations. So shown in this presentation, in this slide, is my outline for the study. First, I'll be discussing the background of the study together with the research design that we used, followed by the results and discussion that we've obtained, and the conclusion that we've gathered in our study. So to begin with, I'll give you some context of what we want to achieve and what we're trying to solve. So of all the innovations in the 21st century, perhaps the most consequential one is the emergence of modern communication technologies. These types of technologies enables us to communicate effectively using digital means. However, such telecommunications base stations, or TBS as I'll now be referring to them now, require continuous operation and uninterrupted functionality. As mentioned earlier, since we rely on these kinds of technologies for our everyday lives, it is crucial for us to develop reliable systems to power our TBSs. These can be achieved through the use of backup power systems, as I will be explaining this slide here, which I will discuss first the currently deployed backup power systems such as lead-acid batteries and diesel generators. While both aforementioned technologies are technologically mature and commonly used, lead-acid batteries and diesel generators have some challenges. Perhaps if lead-acid batteries are only used, it will only cost around 3 million pesos or 53,000 US dollars per year. And if we're going to use diesel generators, while they're cheap, they require fossil fuels which are more environmentally dangerous, and they require frequent maintenance due to its moving parts and are relatively noisy, as we can attest to that. As such, there are some promising deployed backup power systems that I'll be discussing, and it'll be the focus of our study, hence the lithium-ion battery and the fuel cells. As they have all been steadily gained attention in terms of research and development, as they are a good alternative or a candidate for backup power systems. For example, lithium-ion batteries last longer, which makes it more cost-effective than lead-acid batteries, although I'll have to admit that there'll be a talk later by Dr. Carl Odilio on that regard, so please stay tuned to that. On the other hand, fuel cells are more sustainable because they only require hydrogen and oxygen gas as its requirement. So I'm pretty sure that in our audience, you may heard of fuel cells for the very first time. So basically, fuel cells are electrochemical devices that require hydrogen and fuel gas to produce electricity to the form of water electrolysis, of which the byproduct is water. Hence, it's a more sustainable option for backup power systems. As I mentioned earlier, these traditional backup power systems may be cheap and technologically mature, but suffer from environmental concerns. The alternatives, such as lithium-ion batteries and fuel cells, offer the promise of sustainability, but they are hampered by the faster degradation when subjected to fluctuating power demands, as mentioned by my colleague, Mr. Arvin Esotero. This can be addressed, however, by combining it with lithium-ion batteries. However, such addition includes more cost to an already expensive system. Remember, fuel cells are really expensive. And if you're gonna add more lithium-ion batteries, they're gonna make it more expensive. As such, optimal sizing, along with cost-effectiveness and system reliability, needs to be addressed. As such, the solution would be an optimized fuel cell/lithium-ion battery hybrid system, specifically for TBS stations. So the goal now is to optimize the sizing requirements of a hybrid fuel cell lithium-ion battery system for a telecommunication base station using MATLAB Simulink, and I'll be discussing each of the components here one by one. First is the fuel cell characteristics. So since fuel cells are considered electrochemical devices, they can be further simplified into their equivalent circuit model. Shown in on the left side are the equations. I'll discuss some parameters such as EOC, which is the open circuit voltage. N stands for the number of cells per module. A stands for the Tafel slope. And I sub 0 is the nominal exchange current. Shown in this slide is the degradation equations of the fuel cell, as we need to consider the fact that fuel cells degrade whenever there is a fluctuating power requirement. And shown in table 1 are the coefficient values used in the model. In this slide shows the battery characteristics. For example, in table 2 shows the open circuit voltage equation, which is really dynamic and involves a lot of parameters as well. And to consider the degradation of the battery, we utilize these equations, and table 3 shows the pre-exponential factors at different C rates. Okay. So shown in this slide is the bus voltage and controller algorithm specifications. So as we seen the system before, it requires a DC bus voltage, and table 4 shows the specifications of that. And table 5 shows the control rules implemented in the power system controller. So basically, the control rules aim to figure out if the bus voltage, V-bus, satisfies the following conditions. So for example, if the voltage bus is detected to be lower than the controller low voltage trigger, or VL trigger, and if the current state is off, the next state will be at maximum efficiency. And if the V bus is, same again, if the voltage bus is lower than the low trigger voltage, but the current state is max efficiency, the next state should be in max power, and so on and so on. Okay. Another consideration is the cost and lifetime factors of the system. So Table 5 shows the cost and lifetime factors of the fuel cell, the battery, and hydrogen. Okay. So shown here is the results. So fuel cells with power ratings of 3 kilowatt, 4 kilowatt, and 8 kilowatt were selected for the analysis. And the battery capacities are incremented by 1 kilowatt hour as seen in the x-axis of of figure 4 right here. And figure 4 shows the minimum bus voltage for the 4 kilowatt and 8 kilowatt capacity. Okay? It was observed that the 8 kilowatt system was able to maintain the voltage bus even at a small battery capacity, while the 4 kilowatt system required at least 2 kilowatt hour capacity to satisfy for the minimum bus voltage. As we shown in the previous slide, the previous slides right here, the table 4 is the main basis for the analysis in figure 4 in this slide right here. Okay? So next is the results of the simulation showing the fuel cell power loss. That's from left to right, the fuel cell power loss, the battery capacity loss, and the hydrogen fuel consumption. So the results from the simulations show that the power loss, the battery capacity loss, and hydrogen fuel consumption is greater at smaller battery capacities. Okay, so there's that. The cause of fuel cell degradation can be attributed to the on-off stage or the changing output power as seen from the load, or from the TBS rather. And the cause of the battery capacity loss would be the complete discharge. Okay. Shown here in figure 6 is the overall system cost in a 4-day operation. So figure 6 indicates that a smaller fuel cell system is more cost effective since larger systems are still expensive. Okay? So overall, this indicates that a smaller fuel cell system is more cost effective as well. Okay. So for the main insights in our study is that while larger fuel cells are more efficient and reducing hydrogen consumption, they do not justify their high cost. That's why we need to make sure that small capacity batteries can maintain system stability when paired to a suitably sized fuel cell. Okay. For TBS specifically, a smaller fuel cell system with an optimized battery size is considered to be the most cost-effective in terms of minimizing both fuel cell degradation and hydrogen consumption while maintaining reliability as well. And that concludes my study. Thank you for your time. And before I would end, I would just like to acknowledge all the support from the CIPHER project funded by the Commission on Higher Education, Philippine California Advanced Research Institutes, together with aforementioned affiliations such as the Power Electronics Laboratory, the Laboratory of Electrochemical Engineering, and the University of California, Merced, for their endless support and collaboration. Thank you very much. And I'll open the floor for questions.
Thank you, Mr. Manlapas. Are there any questions from the audience? Okay, I just have one question. Are the methods used here for the optimization applicable for other kinds of batteries as well? For example, what if we hybridize lead-acid batteries and lithium-ion batteries?
Okay. Thank you for that question. Perhaps the overall method, the overall system used in the study can be used in different battery chemistries. However, it will all be different when it comes to the modeling. So, of course, each battery chemistry have their own different degradation factors, capacity loss mechanisms, and something and so forth. And that would be applicable as well for fuel cell systems as well, because there are also different kinds of fuel cells, not only mentioned by this study as well. So thank you very much.
Okay, thank you for your answers and your presentation. So if there are no more questions, I would just like to give this certificate of appreciation for Mr. Juan Glicerio Manlapas for sharing their invaluable insight and work on optimal sizing of hybrid PMFC lithium-ion battery power systems for telecommunication base stations during the NEECECON 2024 conference in Quezon City, signed by Dr. Lou Andrew Tria. Thank you again, Mr. Manlapas. Okay. So we have now come to our final speaker for this technical session on electric vehicles and energy storage. Our final speaker is Dr. Carl Odulio. He is a professor and our expert in power electronics and battery technologies from the UPD EEEI. In this talk, he will be discussing the technical analysis of the continuing importance and contribution of lead-acid-based batteries, given the rise of other battery technologies. The title of his talk will be The Continuing Relevance of Lead-Based Batteries, Evaluating Traditional Technologies and the Emergence of Lead-Carbon Solutions.
So this presentation is on the continuing relevance of lead-based batteries, evaluating traditional technologies and the emergence of lead-carbon solutions. We'll be looking at one of the reasons why we decided to have this presentation was because recently we have been doing a project on lead-based batteries, and I think there's a misconception that lead-based batteries are going obsolete. No? So one of the motivations for this presentation is to show why lead-based batteries are here to stay. Specifically, recent technology or modification of the lead acid, which is the lead carbon battery. Okay, so just to give a quick introduction on different battery types, we have different types of applications for batteries nowadays. We have the stationary applications where we use batteries for solar PV systems. We have automotive, as we all know. We use batteries for electric vehicles, and of course our handheld and portable devices. So we have batteries used in cameras and our smartwatches and so on. Okay, so the focus of the discussion today would be on rechargeable batteries, not the primary but secondary type of batteries. And in different applications, the choice of chemistry depends on the density, the cost, environmental impact, safety, and application requirements. Okay, so the two popular technologies right now would be the older one, which is the lead acid, and fairly recent, not really new, the lithium batteries. As we all know, lithium batteries have been very popular, and I think this technology is here to stay, for even if we have been hearing news of scarcity in raw materials. The projection of the use of lithium batteries would be well into the 2050s. Okay? Lead acid, on the other hand, even though if it's an old technology, if you notice, our starter batteries in our vehicles have still been using lead acid, even though there are some lithium that's already being used in some vehicles. Okay, so I think one of the main reasons why lithium cannot really replace lead acid in everything is because of the safety issue. Okay, cost is definitely very relative. Cost can go up depending on the demand. Cost can go down depending on the supply and the demand as well. But one of the selling points for always going back to lithium, to lead, is the safety concern because of the risk of thermal runaway and overcharging. Okay, so even if we use them in our laptops and smartphones, we use them in our electric vehicles too. As you can see here, these are examples of battery failures for lithium batteries. So, now this one is a recent incident involving lithium. This happened about 2 weeks ago. Actually, it's if you look at the image on the right, they were already using an extinguisher for the batteries. But this is a screenshot of a video where you can see the lithium batteries just catching fire without any external, what do you call that? Without anything touching, essentially, the lithium battery. It was just there for storage. And this is an example of how high the risk is for lithium batteries. Okay, so it just caught fire and there were 23 people who died and I think about 20 who are severely injured. Okay, so this is a lithium plant in Korea. Okay, so a few weeks ago. Okay, so lead-based batteries. We have been using lead acid for a long time, for more than 100 years now, since the first electric car in the late 1800s. They are relatively simple energy storage devices based on the lead electrodes. And the problem with this is that they have lower energy densities compared to lithium batteries. Okay, they have lower cycle life, primarily because of the sulfation in the negative electrodes, and this would limit the number of cycles, especially in heavy-duty applications. So the question is, will lead acid die or is lead acid dead? And why still choose it? So some factors would be cost effectiveness. It's still cheaper than lithium. It's well established. It is robust and safe. Actually, you can. It doesn't mean that the batteries will not fail. Lead acid can still have failures, but it is not as bad as the failure of the lithium batteries. So recent developments would be advancements in the performance by adding carbon in the negative electrode. Okay, so this gave rise to the lead-carbon batteries. They would still have the lead oxide in the positive electrode and activated carbon in the negative electrode. So this is the same technology used in supercapacitors. So this addition to the lead-based battery actually prevents the sulfation in the battery. So this would enhance the performance, the overall performance of the battery. It improves the cycle life. It improves the overall discharge and charge characteristics of the battery. So these are just some curves from a 24 ampere hour lead carbon battery. If you look at the image on the right, the capacity as a function of discharge rate. So technically, if you will compare, I forgot to add the performance of lead acid. So for lead carbon, if you look at the capacity here, we discharge the battery at a 10-hour rate all the way to 1 hour. Okay, so 10 C over 10 all the way up to 1 C. And if you will compare this to lead acid, at 1 C discharge rate, meaning you discharge the battery, if it's 24 ampere hours, you discharge it at 24 amps. At that rate, the capacity you will get is actually already going to be about 50% of the rated capacity for standard lead-acid batteries. If you look at the numbers here, the 24 ampere hour battery actually still gave us 20 ampere hours. Okay, so 20 ampere hours is, ilang percent ba yun? Around a little over 80%. No? So it's a lot better than lead acid. So this just shows that it's very similar to different types of batteries. As you operate at a higher temperature, capacity goes up. Lower temperature, capacity goes down. So this is similar to other batteries. The one on the right is the cycle life as a function of DOD. If you look at lithium batteries, you would normally be using them up to about 80% DOD. For lead acid, the recommendation is about 50% DOD. And if you look at the lead carbon, the recommendation is to about 70% DOD. So 70% DOD means you can discharge it way further than the lead acid, and it is very close to the recommended operating mode of the lithium. But if you look at the performance, actually, here at 100% DOD, you can still get around 800 or maybe 900 cycles, which is way better than what you would get in lead acid. Okay, so this is actually already close to how, well, not really close, but it's nearer the performance of lithium. It's farther away from lead acid. So self-discharge rate is basically what the capacity of the battery would be if you do not use it. You just leave it on the shelf and then you pick it up again after some time. So it's just better. It's not as good as lithium, and it's a little bit better than lead acid. But there's a big difference between how lead-based batteries are stored. Because when you leave lead-based batteries, you do not want to leave them unconnected. Unlike a lithium-based battery where if you fully charge them, you would want to disconnect them because it will decrease the life of the battery, which is similar to cell phones, right? So if you fully charge your cell phone, you do not want to leave it connected to the charger. You have to remove it from the charger. And lead-based batteries would prefer to operate at a floating voltage. So this is why, even if you have this characteristic in stationary applications, the lead battery would always be connected to some power source, whether it's solar or some trickle charger is connected to the line or to the generator. Okay, so cycle life at different levels of DOD. Okay, so lead acid here, it's really very low. That's less than 1,000 cycles. Lithium, this is really highly theoretical. So, wala namang gumagamit unang-una ng lithium at 40% DOD. And wala pa nakakapag-prove na umabot ng 12,000. But this is a projected cycle life. Okay, so essentially, if you look here, they are very close to each other. Okay, so the lead carbon battery at around 70% is somewhere 2,000 something cycles, and the lithium is about 3,000, or maybe 3,000 thereabouts. Okay, so what's the difference? For the lead acid, 500 to 1,000 cycles. Lead carbon is 1,500 to 2,000. Lithium is 2,000 to 3,000. Recommended DOD is 50%, 70%, and 80% respectively. Specific energy is 30, 40, and 128. Okay, so which is why the lead-based batteries are not really recommended for mobile applications. So they're really good for stationary applications because you don't want to have a very heavy battery for mobile applications. Efficiency, 70 to 85, 90, 90 to 95. Cost, the lead carbon is somewhere in between. Recyclability, this is where you have a very good performance from the lead-based batteries because they can be recycled up to 98%. Okay? Lithium ion is recyclable, but the problem is there's no critical mass right now. So it's very expensive to set up a recycling plant for lithium ion, and but well, probably one day we will get there. Okay? So safety, generally safe for the lead-based, and lithium, you always have that risk of thermal runaway. So some notes for the conclusion. Lithium batteries are known for their superior energy density compared to other technologies, but they are still relatively expensive, face challenges with raw material scarcity, and might be excessive for applications where high performance is not a critical requirement. Lead-based batteries, including lead acid and lead carbon types, are still suitable in applications where weight is not a primary concern. And lead acid batteries are still the most cost-effective option for rechargeable applications that do not demand high performance. And lead carbon batteries represent a significant improvement over traditional lead acid batteries in terms of cycle life, cycle efficiency, and state of charge, while retaining the robustness of lead acid technology. Thank you very much.
Thank you, Dr. Dulio. Are there any questions from the audience? There's one question, sir.
Earl Wanico po from UP Diliman AI program. I just want to ask, I'm curious about kasi carbon, I think has already been used even sa zinc carbon batteries, which have been around earlier than lithium-ion batteries. So I saw kasi the references na nandun sa footnote, 2022. So why only now that carbon has been integrated with lead-based batteries, why not earlier? So any motivation or any development?
As to why, I don't know why really, but the infusion of carbon, I think, dates back to 2017. That was the first time I saw it used in lead acid. And it had a good performance, but I think one of the reasons that it really did not take off was because lithium was really the more popular battery at that time. No, actually, the company that started this in 2017, binenta nila yung technology. So they closed shop and they sold the technology or the rights to someone else, and someone else is using that in the manufacturing yung lead carbon. No? So I really cannot say kung bakit hindi before that. But yeah, it's not really 2022 when they started, but almost around 7 years ago. Maybe even before that, no, for R&D.
One last question. Where do you see the future of lead carbon batteries, like especially in battery energy storage systems? Kasi halimbawa, if EVs will be rolled out eventually, there needs to be charger along the highways, like NLEX or SLEX. But these are far away from the city. So do you see a future for lead carbon batteries in, I don't know, microgrids where, they are isolated areas, but you still need some charging going on? Maybe if it's integrated with solar or other types of energy harvesters?
I think lead carbon has potential future for solar PV systems. we are going to deploy lead carbon in a project that we are doing right now for solar PV. Okay, there is also a plan to do it for e-trikes and two-wheeled electric vehicles, but I am not very excited about that simply because of the weight problem. Okay, you can use it definitely, but I think the future of lead carbon would be to replace technologies for stationary applications. So there is a good chance na may potential siya sa stationary applications.
Thank you po.
Thank you. Thank you.
Are there any other questions for Dr. Odulio? Okay, if there are none, I would like to give this certificate of appreciation to Dr. Carl Michael Odulio for sharing their invaluable insight and work on the continuing relevance of lead-based batteries, evaluating traditional technologies, and the emergence of lead carbon solutions during NEECECON 2024. So I would again like to thank the presenters for their presentations and their answers to the questions. I hope we all learned today about the newest academic and industrial development in electric vehicles and energy storage systems. Hopefully we can all participate again tomorrow. So before we go, I would like again to extend our heartfelt gratitude to Advanced Energy, Techmark Keysight Technologies, Embedded Silicon Technology Solutions Corporation, Meralco, Analog Device Incorporated, Presidium PH Corporation, Road & Schwartz Philippines Incorporated, Alexan Commercial, Maker Lab, Samsung Electronics Philippines Corporation, and Challenge Systems Incorporated for their invaluable support to the NEECECON 2024. So again, I would like to thank you all for participating, and I hope we can all participate again tomorrow. Thank you.